4.2.24. For this problem, we're looking for where the function f equals cosine squared x. We're looking for where the function is increasing and decreasing on the interval negative pi to pi. To do this, we need to find f prime. And the reason for that is f prime gives us rate. And if a function is increasing, its rate will be positive. If a function is decreasing, its rate is negative. Conversely, if the rate is positive, we know the function is increasing. If the rate is negative, then the function is decreasing. To do this, I recommend writing f differently. If we write f as cosine x, quantity squared, then it is clear we use the power rule combined with the chain rule. So our interval is negative pi to pi, our function is cosine x, quantity squared, and we're looking for f prime. To find f prime, I bring the 2 down, so it's 2 cosine x, and then the power is 2 minus 1, so the power is 1, and then chain rule times the derivative of cosine x. And the derivative of cosine x is negative sine x. And I just bring the negative out in front. I could at this point use the double angle formula. 2 cosine x sine x is the same as sine of 2x. I could do that, but it doesn't really help the problem. In fact, I think it's a little bit easier to do the problem with it written like this. So I'm going to leave it. F prime is defined on the given interval. In fact, f prime is continuous not only on the interval, but for all real numbers. So the function f is differentiable for all points on the interval. And it's not only differentiable, the derivative is continuous, as I said. So in order to find critical points, we set f prime equal to 0. And the reason why I talk about this differentiability is that you may remember a critical point is a point either where the derivative does not exist or where the derivative equals 0. And since the derivative exists everywhere, if there's a critical point, it has to occur where f prime equals 0. So what values of x make f prime equal to 0? Using the 0 product rule, a product is equal to 0 if and only if one of the factors is equal to 0. So if f prime is 0, then either cosine x is equal to 0 or sine x is equal to 0. If cosine of x equals 0, then x has to be negative pi over 2 or pi over 2. Of course, there are an infinite number of points on which cosine x equals 0, but those are the only 2 points on the given interval. And sine x equals 0 on the interval for x equals 0, negative pi, and pi. A very small point, but you may recall part of the definition of being a critical point is it has to be a point on the interior of the interval, and end points are not interior points. So I ignore the answer pi and negative pi. However, I am aware that my derivative equals 0 there. So I take these remaining 3 points, negative pi over 2, 0, and pi over 2, and I break my interval negative pi to pi. I break my interval up according to those critical points, and I end up with 4 intervals on which I need to look. Now, I just want to point out that these are the blue markings are the only places on the interior where f prime changes from positive to negative or negative to positive. And the reason why that's important is that if we choose a test point like this, if we choose a test point for each interval, and we test whether or not f prime is positive or negative for that point, that test point tells us what f prime is for the entire interval. So, for example, f prime is negative at negative 3 pi over 4. Since f prime is negative at that point, it's negative for the entire interval, because if it were to switch from negative to positive or positive to negative, then we would have found another critical point. And so all we need is a test point for each interval, and I always choose the easiest possible test point. The test point has to be on the interior of the interval, just to make that clear. I like to use a diagram to help me keep my information straight. So when I have f prime is negative, I use a downward slant. When f prime is positive, I use an upward slant. My slants are connected by these open circles. And then that, I don't know, I just like it. It helps me to keep my information straight and to kind of see vaguely what the graph might look like. So my function is decreasing on the first and third interval, and it's increasing on the second and fourth interval. And I'm using open parentheses, so I use the curved parentheses. Use open parentheses because at the actual critical points and at the endpoints, recall that my derivative is actually 0 there. So it's neither increasing nor decreasing at those points. All right, take care. I'll see you later.